Well, we got what we got. We better get rolling. So we start a new, well, still the same chapter, okay? Still dealing with heat, but it's kind of a new concept or a new series of concepts. Y'all ready? We'll throw out the word enthalpy. Makes me think of a speech impediment. Like you're implying enthalpy. That's what it makes me think of, but that's the word. We should pray. Father, Lord, help me to be clear and concise, to convey these things in a way that everybody can understand. Help me to teach with compassion and with love. Please help us as we're learning these things to just to even know if we know what we're learning, or to real understanding and humility to ask questions when we need it. And help us to remember these things in the times that we do need them. We pray this in Jesus' name. Amen. All right, so enthalpy. What do we want to say about this? First of all, one thing you need to know is that the total of all possible kinds of energy present in a substance is called its internal energy. This is our main theme. We're going to get there. We're going to build to it. So, internal energy is all energy in a substance. All forms. It could be kinetic energy, things moving. Could be potential energy. Could be all forms. It says here, as a system undergoes a change, its internal energy can change. And energy can be transferred from the system to the surroundings or from the surroundings to the system. We've kind of been looking at that, right? It says energy is transferred into a system when it absorbs heat from the surroundings and or when the surroundings do work on the system. For example, energy is transferred into room temperature metal wire if it is immersed in hot water. So we can just directly add heat by putting it into boiling water. I can also add heat to a wire simply by bending it back and forth, and it'll heat up, right? Okay. Friction's a good source. And these are ideas here that you're doing work on the system, right? Moving it back and forth. I'm taking energy from my body and converting it into a mechanical energy, which is then going to convert it into a kinetic energy, which is then going to convert it into heat energy inside of that. Friction's another one, right? You can be cold, and you can sit here and you can go like this and literally heat things up. Okay. The relationship between internal energy, heat, and work can be represented by the following equation. So where this is change, right? Delta change in internal energy. Equals Q. What is our Q?
Energy.
What's it been always? It's a specific type of energy. It's been heat. Okay. Heat. We've been measuring it joules for sure. Heat plus work. Okay. So if I add heat or if I do work on something, that's going to change its internal energy. Of course, this can go both ways, right? I can reduce internal energy by taking it to do work or taking heat from it. This is one version of the first law of thermodynamics, and it shows that the internal energy of a system changes through heat flow into or out of the system. Okay. What else do you need to know here? State function, this is a term that's going to come up a little bit, okay? Basically just giving you some vocabulary and some basic terms that we're going to be using during the rest of this unit, okay? So, state function is any function where its value depends only on the state that it's in. Right now, I'm going to go back and read this. The relationship between internal energy, heat, and work can be represented by delta U equals Q plus W, right? Internal energy is an example of what's called a state function or state variable, whereas heat and work are not state functions. The value of a state function depends only on the state that the system is in and not on how that state is reached. So, this has a certain amount of energy right now, okay? This has potential energy, yes? If I drop it, it will release, it will convert that potential energy. It has, as long as it's at this height, actually I'll go with this height. As long as it's at that height, it does not matter how it got there. All that matters is that it is in that state. There are a number of ways that I can get this here. I could have it up here and drop it, and then it actually lost energy to get to that, right? I could have it down here, and I could lift it directly. I could have it here, and I could, we could play hot potato with it all over the room and have it land over here. A lot of energy transitions were done, but none of that matters. All that matters is this is where it's at right now, okay? So the idea of a state function is it doesn't matter what was done to it to get it there, only that it is there, okay? There are other things, if we were to look at like the distance traveled, that's not a state function, right? So if I lift it up, then the distance traveled, which is not a state function in that case, is how much? Estimate. About a meter, right? But if we tossed it back and forth, the distance traveled is 1 meter plus at least 3 plus another 3 back, right? So it's at least 8 meters. So distance, not a state function. Potential energy here, state function. Okay? That's the idea. All right, let's roll to the next concept. Chemists ordinarily use a property known as enthalpy to describe the thermodynamics of chemical and physical properties. Enthalpy is defined as the sum of the system's internal energies and the mathematical product of its pressure and its volume. So we're going to go here. So enthalpy, H, equals U plus PV, where U, coming from over here, is its internal energy. Plus its pressure and its volume. Okay? So enthalpy H equals internal energy plus pressure times volume. Enthalpy is also a state function. Enthalpy values for specific substances cannot be measured directly. Only enthalpy changes for chemical or physical processes can be determined. Mathematical product, P delta V represents work, W. So now, here's what, I better back, I skipped a step or two. Let me read the whole thing. Enthalpy is a state function. Enthalpy values for specific substances cannot be measured directly. Only enthalpy changes, chemical and physical can be determined. For processes that take place at constant pressure, then the enthalpy change, delta H, enthalpy change delta H is change in U plus P delta V. Okay? So we're going to assume a constant pressure. Okay? We cannot assume a constant volume. If we're doing this in chemical equations, we might be changing from solids to liquids to gases. The volume is going to change quite a bit, right? This should be constant, so a change will essentially negligible. A change in our enthalpy, our total energy of the system, is equal to a change in the internal energy plus a change in multiplication of the change of the volume times the pressure. Okay. The mathematical product of pressure times volume represents work. So this is the next concept here. P delta V equals work. By their namely expansion or pressure volume work. So, what do I mean by that? If I had a balloon and the balloon was just regular and deflated and I wanted to inflate it, I have to do work on that system, right, to change its volume. In the same way, if I had a chemical reaction and I did it in a little test tube and I had a balloon over it and that balloon blew up because of the gases coming from that chemical reaction causing it to expand, that chemical reaction did work, right? Okay, so it may change. I don't know if you've ever done this, but you take baking soda and vinegar, right? And you're used to it fizzing. Well, that would actually do work, right? It would blow up a balloon, okay? But the other thing about that is it gets cold. Like the liquid, if you were to do this in a test tube, all right, and you start off at room temperature, and then you did this, the liquid is actually going to feel colder, less hot, okay? And so there's some significant changes here. There's going to be a change in this, which is essentially, we're dealing with this, and there's going to be a change in my work. So there will definitely be a change in the total amount of energy of the system. There will be a change in my enthalpy. Okay. All right. We are going somewhere with all this. This is just the conceptual framework for the math we're about to do. Substituting this equation and the definition of internal energy into the enthalpy change equation yields this. Now I'm going to erase some stuff so I'm going to write. Okay, so we start with delta H equals delta U plus P delta V. We've got that. That's over there. It's, okay. Then we start substituting in some values. So we get delta H equals QP plus W minus W. Why? Okay. I got to make sure that I know why it's saying this, because P delta V equals negative W. So that's where this this yields this. Okay? The work done by changing the pressure of the volume is coming from here. QP plus W. Oh, that was our formula over here, right? Equals Q plus W. So we already had that one. So we've got a double substitution in here. So this is coming from one side, this is coming from the other. Well, we know these are going to cancel out, right? And so we end up with QP. So delta H equals QP, where QP is the heat of reaction under constant conditions of constant pressure. Fair enough? Okay. So for all intents and purposes, this is a mathematical proof for how we're going to get where we're going. For all intents and purposes, when we deal with enthalpy right now, we're going to be dealing with the heat associated with it. Negative value of enthalpy change indicates an exothermic reaction. So if this is negative, then it's exothermic. If this is positive, then it's endothermic. You guys know those terms? What is an exothermic reaction going to feel like? Hot or cold? Exothermic. What does exo mean? Exoskeleton. You find those on bugs. Where's that skeleton? Outside. So this is exothermic, outside heat. So this is releasing heat outside. This is going to feel hot. Endothermic, this is bringing the heat inside. It's going to feel cold because it's going to take your heat and put it inside of the system, right? So these feel hot, these feel cold. These release energy, these absorb energy, okay? That's maybe something else we want to see. These release energy, release heat. These absorb heat. Very typical exothermic reaction would be combustion of gasoline. You light a fire or something like that, it releases heat. But there are plenty of other reactions that are endothermic. They require energy. They take energy in as they're doing their thing. All right. This is a lot. I just want to do math. Never said that in my life. I just said it down. A negative value of enthalpy change indicates exothermic, positive indicates an endothermic reaction. If the direction of the chemical equation is reversed, the arithmetic sign is also changed. We'll be dealing with that coming up. We'll have something where you've got a chemical reaction and you've got a delta H for it, but for necessary reasons you'll flip that thing. We're going to hypothetically run this reaction in reverse. That means maybe instead of releasing energy, if you wanted to go in reverse, you'd have to add energy. Okay? All right. Enthalpy change of reaction depends on the physical states of the reactants and products, so these must be shown. So we're going to show whether it's a gas, a liquid, a solid. In fact, when we get some problems later on in this, we'll go from like hydrochloric acid as a gas to hydrochloric acid as a solution. And so you have that there's an energy change associated with that, and we've got to account for that. Okay, so that's why they're mentioning that. Oh, good. Okay, let's do something with this. Anything that does not make sense at any point, please just speak up, okay? I'm feeling myself feel anxious and just want to get to it, and that may not be best for you. So if I've messed up in doing that, just talk to me. All right. When 0.0500 moles of HCl, aqueous, reacts with 0.0500 moles of NaOH, aqueous, to form 0.0500 moles of NaCl, aqueous. It says that 2.9 kilojoules of heat are produced. Okay. Write a balanced thermochemical equation for the reaction of 1 mole of HCl. Okay. So let's write out just what the hypothetical reaction would be. There's nothing complicated about this, right? So what are the two things this should be HCl. So what are my what are my reactants?
HCl.
HCl plus
NaOH.
NaOH yields
NaCl.
NaCl plus
Water.
H2O. Good. Right, this is a neutralization reaction. Strong acid plus strong base equals salt plus water. Okay. All right, good. Now, what we want to know is what the delta H is, okay? So when I add these two things together, there's going to be some energy change associated with this. First of all, is this going to get warmer, or is the liquid around it going to get warmer or cooler? Look at this. Positive value here. What does that tell you?
Warmer.
It's going to get warmer. Okay. All right. One second. Well, no, it's actually going to be opposite. So if this is a positive value, it gave off energy, or I'm sorry, if this is a positive value, that means it absorbed energy. This reaction, the system gained energy from its surroundings. It's kind of counterintuitive. If this was a negative value, that meant that it gave off energy to its surroundings, right? So we'd expect this, as we would take it, we'd expect this to feel colder, okay? All right, so here we go. HCl plus NaOH gives that. Now, I have numbers for a small quantity, right? I want to get it for I want to get it for 1 mole. So, we're dealing with HCl, right? So, where's my HCl? My HCl is right here. So, I want to get from that to that, right? So I need 1 mole of HCl times, okay, 0.0500 moles of HCl. It's basically just a ratio. I know that for every 0.500 moles of HCl, I get 2.9 it takes 2.9 kilojoules. Right? And so I'll get you calculators. So we're going to divide 2.9 by should get what, 58 kilojoules?
Yeah.
Okay. Let's see what this is.
Well, you wouldn't have to convert the kilojoules to joules in the equation.
Not for this. No, in all of these, they almost always want in kilojoules. So, yeah. Okay. Good question. And that's the answer. That wasn't hard, right? Okay. Well, let's roll on to the next one. Okay, next problem. This is, if anybody's watching at home, this is example 5. Well, it's still on 5.8. We're doing the second part of it. So when 1.34 grams of zinc as a solid reacts with 60 milliliters of 0.750 molar HCl aqueous. The delta H is 3.14 kilojoules. Okay. Determine the enthalpy change per mole of zinc. So, in other words, what is delta H for 1 mole of Zn? Okay. All right. So, how will I go about this? I want to get, we've got this to start with, right? 1.34 grams of zinc solid. And I'm trying to get to an amount of energy, right? A delta H. So what do I need to do?
Transform into moles.
Okay. So I need 1 mole of Zn. Somebody's going to look at a periodic table and tell me the mass of 1 mole of zinc.
65.39.
65.39 grams. Okay.
No opposite?
Hmm?
There's no grams on the bottom and moles on top.
Oh yeah, sorry, thank you. I can't be trusted. Okay, so run me that number again,
65.39.
65.39?
Yeah.
Okay, 65.39 grams per 1 mole of zinc. Okay? All right, so at this point I have 1 mole of zinc. The other thing that I need is that, right? So I can do it this way, actually. I've got 1.34 grams of zinc over 3.14 kilojoules. This is just a ratio, right? The same as we say grams per mole, that's just a ratio. Same thing here. I've got this many grams equals this many kilojoules, so I can throw those, since they're on opposite sides of an equal sign, I can throw them up there as a ratio. I know that when I multiply this out, I'll get, oh, I've got it backwards of what I want though, don't I? I've got moles per kilojoule, so I need to flip this whole thing, right? I need kilojoules per mole, so I want to go 3.14 kilojoules over 1.34 grams of zinc times 1 mole of zinc over 65.39 grams. That will get me kilojoules per mole. That's what I want. So let's run those numbers. What'd you get?
How can you use the 3.14 kilojoules as a ratio to the zinc when the whole reaction is you're just completely disregarding the HCl? No, because doesn't the HCl also help produce the 3.14 kilojoules?
Yeah. So,
So
okay.
how can you do the ratio of zinc to joules
Yeah.
produced without?
Okay. So this, as you point out, is obviously representing the entire reaction, right? It's the energy of the entire reaction. But if I have this amount of zinc, now, they're assuming that I don't have a limiting reagent here, or at least that this is, that the HCl is not a limiting reagent. Although that may be a mistake, maybe I made a mistake there. Hold on. Give me 1 second, make sure that I haven't made a mistake. We're going to be safe right now to do what I'm doing, but it's going to come up later where I do have to make sure that one of these is not a limiting reagent, okay? But because it's giving me a quantity here and another quantity here for 1 mole, it's safe for me to assume at this moment that this is not a limiting reagent, okay? So for every 3.14 grams of zinc, I will get this much of this. The question is simply, if I had, assuming I have enough HCl to react with 1 mole of zinc, then how much energy will I get? If I doubled my quantities here, what's going to happen here? It's going to double, right? It's literally just a ratio. And so I'm looking for, okay, I'm not doubling it, I'm going to bring it to 1 mole. I don't know off the top of my head what ratio that is, but it's, you know, it's going to be pretty good. It's going to be like 40 times bigger or something like that, right? Then how much bigger is this number? Well, it's going to be something like 40 times bigger when I'm done with the whole thing. Does that answer the question?
Yeah,
So I'm not looking at the energy of zinc. I'm looking at the energy of the reaction, right? And here I'm not worried about the energy of 1 mole of zinc. I'm worried about the energy of the reaction that would happen if I had 1 mole of zinc. Okay. So what is this number?
Oh, 153.22.
153.22.
22.
Okay. Everybody get that same answer? So did I. Okay. I got 2.3, but whatever.
Yeah.
Okay, 153.23 kilojoules, right? Let's make sure that that's what they have. It is. And they did sig figs to get to 153 kilojoules, which makes sense because I've only got 3 sig figs anywhere. So 153 kilojoules is our answer here, okay? Well, we're going to build on this. We go to the next one. All right. Writing thermochemical equations. It says a gummy bear contains 2.67 grams of sucrose. So 2.67 grams of C12H22O11. When it reacts with 7.19 grams of potassium chlorate, potassium chlorate, KClO3, $43.7 kilojoules of heat are produced, right? So my sign here, positive or negative? Energy is released, my sign is?
Negative.
Negative. Right. Okay. All right. That matters. It says write the thermochemical equation for the reaction of 1 mole of sucrose. All right. First of all, what does my equation look like? I've got C12H22O 22O11 plus KClO3, and it produces a couple different products, 12 CO2s, this is gaseous, plus 11 waters as a liquid, plus 8 KCl's, aqueous. All right, this is a solid, or is it in solution? It's given to me in solution, okay, aqueous. This is aqueous. All right, so that's my reaction. What I want to know is what is my delta H, right? So, again, we're going to use this ratio concept. It says, unlike the previous example exercise, this one does not involve the reaction of stoichiometric amounts of reactants, and so the limiting reactant must be identified. So I got to know which one of these is my limiting reagent. Okay? So, you all know how to do that, right? I can do either one of these, either number to figure out which one. Actually, I need to do both, don't I? So if I go 2.67 grams, where is that? Let's just figure out moles. I need 1 mole of this to 1 mole of this, right? So let's just figure out how many moles we have, and then we'll know which one's limiting, okay? So 2.67 grams times 1 mole over however many grams. We'll do it for that one, and then we'll do 7.19 grams over however many grams per 1 mole of this. Okay, so let's go 12 times 12 plus 22 plus 11 times 16 equals 342. And that again, because I don't trust me, so 144 plus 22 plus 11 times 16 is 342. Okay, and somebody have KClO3? I don't have that. Probably pull off ClO3, but I don't know potassiums.
122.55.
One more time?
122.55.
122.55.
Yeah.
Okay, so let's do the math on these. So you guys do this one, I'll do this one. We'll meet in the middle. Okay, that one's good. Over here.
0.008.
008. Whoa,
That's what I got.
that's not that much, is it? Okay. Is that right? I don't think that's right. Something's off. We have the wrong limiting reagent based on what we just did. I'm missing a 0 here. Okay. Well, now. I'm getting a headache here. Literally. Unlike the previous example exercise, this one does not involve the reaction of stoichiometric amounts of reactants, and so the limiting reactant must be identified. It limits the yield of the reaction and the amount of thermal energy produced or consumed. The provided amounts of the two reactants are, and we did that correctly, we have correct answers. That says the provided molar ratio of perchlorate to sucrose is then 0.0587 moles of potassium chloride per 0.00780 moles of, so they went reverse to figure out, well, if I have this much of this, how much should I get here? They're saying it's 0.00780 moles of that. And that ratio equals 7.52. The balanced equation indicates 8 moles of KClO3 are required for reaction with 1 mole of sucrose. Since the provided amount of potassium chloride is less than the stoichiometric amount, it is the limiting reaction, and it may be used to compute the enthalpy change. Okay. Here we go. So my delta H for my reaction here. I want 1 mole of sucrose, right? Times. I got 8 moles of potassium chloride over 1 mole of sucrose. Is that the deal? So we need that divided by 8. Because it's a 1:8 ratio, which then makes this the limiting reagent. I'm just, you know what? I don't get it. And I did this problem. It wasn't a problem then. That is the problem. Okay, so 1 mole of sucrose times a mole-mole ratio. So now I'm dealing with moles of potassium chlorate. Now I can take this and I can deal with this. So I've got 122.55 grams of potassium chlorate per 1 mole of potassium chlorate. And now I can multiply that by, when I have 7.19 grams of potassium chlorate, I have an energy yield of negative 43.7 kilojoules. Okay? Let's go back and look at this. It wants to know how much energy what's the energy change associated with the reaction of 1 mole of sucrose. To do that, I go 1 mole of sucrose. I use a mole-mole ratio to get to moles, for 8 moles of potassium chloride. Now I use the molar mass of that to get to mass of potassium chloride. Then I use my ratio of energy release when I have this mass of potassium chloride, or chlorate, and now I will end up with an answer in kilojoules, which will be the delta H. So what is my delta H for this? All right? Negative 5960 kilojoules. Okay. Let's do the follow-up problem here. When 1.42 grams of iron reacts with 1.80 grams of chlorine and 3.22 grams of ferrous chloride, solid, and 8.60 kilojoules of heat. Okay. What is the enthalpy change for the reaction when 1 mole of iron chloride is produced? So this is what it is when I have that mass. I want to know when I have 1 mole of iron chloride produced, what is my delta H? Okay. So the first thing I gotta do is figure out my limiting reagent, right? Let's make sure that I haven't written the formula wrong this time, because that would be bad, right? Okay. Iron. Iron chloride, that tells me that this is a +2, right? I need 2 moles of this for every 1 mole of that. And was this gas or was this aqueous? It didn't tell me. It did not tell me. I've got to assume that this is aqueous. When 1.42 grams of iron, I'm going to assume this is solid. I wish it gave me more information, but it doesn't. No, that wouldn't make sense. That would have to be. All right. It is what it is. All right. I'm assuming this is not diatomic chlorine gas. Okay. So I've got 2 chlorines for every 1 iron, right? So what do I have to have over here? If I were to write out my formula, I know I've got Fe plus Cl yields FeCl2. Iron's good. I got to put 2 in front of my Cl, right? Okay. So now I can go to work finding my limiting reagent, right? So iron, 1.42 grams over the 1 mole over whatever the molar mass is of iron. What is that number?
$55.845.
55.845. Okay, somebody run that number. You run that number for me, Ben, run it twice, and then I need to know my moles of chlorine. So I've got 1.80 grams over, what is it, 35.5? For 1 mole? Yeah.
35.5.
Okay. So, some of you will run this number, run it twice, let me know what these numbers are.
I got 0.025.
0.025.
4275226.
I don't need all that. All right. This is good?
That's up to you.
I mean, that's what you got. These numbers are correct.
Yeah.
Okay. What do you got, brother?
I got 0.0507.
0.0507. Go ahead and give me the last one so I have the proper number here. 025, what's the next digit?
0.54.
4? Okay. Okay. All right. Now remember, I need 2 moles of this for every 1 mole of that, according to this formula, so I got to divide that by 2. And when I do that, I should get, what, like 0.02535 or something like that?
Yeah.
Okay. So boy, these are really, really close. But this looks to be the limiting reagent by just a hair, right? So we're gonna go ahead and work with that. I'm gonna erase things over here. All right, now how do I set this problem up?
One mole
1 mole of?
FeCl2.
Well, it wants, if I'm reacting 1 mole of, oh yes, it is FeCl2. Thank you. FeCl2 times?
Put 2 over 1.
Okay, give me units, the labels.
2 moles
2 moles of
Cl.
Cl over 1 mole of FeCl2. Okay? And so now I need to deal with molar mass, right? So 1 mole of Cl has a molar mass of 35.5.
Yeah.
Okay? And now I need to come over here and do this is the mass of that. I need a ratio, right? So
1.80.
1.80 grams of Cl per
8.6 kilojoules.
8 point, is it 8.6 or is it 80.6?
It looks like.
8.60 kilojoules, and remember that my sign is negative, that matters, I gotta have that. Okay, so run those numbers. So what did you get, brother?
Negative 339.2.
Okay. Not 338. Perhaps rounding that is the one that did the difference. All right. 338, 339. It's going to be within a half a kilojoule either way. Okay. Everybody got that number? Good. Okay. Time is it?
Half past.
Holy smokes. All right, y'all. Enthalpy changes are typically tabulated for reactions in which both reactants and products are at the same conditions. They call this a standard state. So, enthalpy changes are typically tabulated for reactions in which both the reactants and products are at the same conditions. So, reactants and products at the same conditions. Okay. A standard state is a commonly accepted set of conditions used as a reference point for the determination of properties under other different conditions. For chemists, basically the standard state is 1 bar of pressure is roughly equivalent to 1 atmosphere of pressure and 1 molar concentrations. since the usual but not technically standard temperature is 398.15 degrees Kelvin, this temperature will be assumed unless other temperature is specified. Thus, the symbol delta H with this little 0 superscript, or O superscript, is used to indicate an enthalpy change for a process occurring under these conditions. The enthalpy changes for many types of chemical reactions and physical processes are available in reference literature, including those for combustion reactions, phase transitions, and formation reactions. So we discuss these quantities. It's important to pay attention to the extensive nature of enthalpy and enthalpy changes. Since the enthalpy change for a given, in other words, the more of something, the more enthalpy change you'll have, right? For these reactions that we've been doing, if we doubled it, we'd have a double the change in temperature. It's not just a steady thing. Since the enthalpy change for a given reaction is proportional to the amounts of substances involved, it may be reported on that basis. In other words, enthalpy change per mole, and that would be an intensive property. That would be something I can use no matter what. Okay? However, we often find it more useful to divide one extensive property by another and report a per amount intensive value of delta H, normalized on a per mole basis. Standard enthalpy of combustion is the enthalpy change when 1 mole of a substance burns vigorously under standard state conditions. So they're giving this as an example. So it's saying here that delta H O for combustion, okay, is the energy change when 1 mole of a substance burns or combines vigorously with oxygen under standard state conditions. So if I take C2 H5OH liquid, which is ethanol, and I burn it with oxygen, okay, I will get CO2 plus water. It's pretty standard stuff, right? This is a gas, this is a gas, okay. And so what it's saying, for every 1 mole, if I'm at these conditions, then I will produce, the delta H will be negative, because it's giving off energy, 1366.8 kilojoules. Enthalpies of combustion for many substances have been measured. A few of these are listed. Many readily available substances with large enthalpies of combustion are used as fuels, including hydrogen, carbon, blah, blah, blah. You don't need all that. You do need this chart. Let me go grab this chart. I made copies, and then we'll do some problems with it. Okay. Let me just stop. Here's the deal. Here's what's coming up with this. There are reactions. Ultimately, we're going to get to. Remember, we talked about this idea of a state reaction. It doesn't matter how we got there. It just matters where we're at. Okay. So there are times that we're going to have coming up quickly, that we're going to have a chemical reaction that we're going to be looking at. And ain't no way that we can carry out this chemical reaction. Like, we're not just burning stuff in this class or whatever, right? Or sometimes you might told to calculate something for burning, and you know, it's just so exothermic it would, you know, would just destroy the building or something like that. Like, we're not going to set off TNT, but we could figure out the energy in a given amount of TNT. If we knew, here's the thing, is we have calculated known quantities. If I have 1 mole of this, then it produces, in this particular reaction, it produces this much energy. And we can go stepwise to figure out, well, how much how much energy is in this substance, like TNT. Okay? If I know the energy that goes into each step, that'll be dealing with something called Hess's law. It'll be coming up. So knowing these for different reactions is very, very useful, because then I don't actually have to carry out the reaction to figure out. I just have to do math. I've got to have a good, reliable chart, and I've got to do math. And I can figure it out. And I got to use my brain, because sometimes it gets a little complicated. But that's where this is going. I just want you to have your head in that. Otherwise, you know, it's just tedious. Like, why are we doing this? It is very, very useful. All right. Let's do this. Okay. Determine the approximate amount of heat produced by burning 1 liter of gasoline. Okay, so I've got 1 liter, 1.00 liters of gas, plus basically excess O2, okay, to produce some CO2 plus H2O, okay. Determine the approximate amount of heat produced by burning 1 liter of gasoline, assuming the enthalpy of combustion of gasoline is the same as that of isooctane. So you got to look on that chart and tell you what's the enthalpy for isooctane. So let's write out this formula. C8H18 liquid plus 25 over 2 O2 gas yields 8 CO2 gas plus 9 H2O gas, right? And then my delta H on that is what? Negative 5,461. So when I burn isooctane, I produce this much energy, right? It's a negative sign, so I know this thing is releasing energy. Okay. And it's giving me something I need to know here. I know that the density of isooctane is 0.692 grams per milliliter. Okay. So I've got a formula, I've got a density, I've got a volume that I want to figure this out for, right? So how do I go about this? I'm going to start with 1 liter, right? So 1 liter of, I'm just going to call it iso. And I don't have liters anywhere else, right? What do I need to get to?
2 moles.
I got to get to moles ultimately. But how am I going to get out of liters?
Transform to grams by using the density.
Yeah, but that's got to put it in milliliters, right?
Mm-hmm.
So first thing I got to do is get from liters to milliliters, right? So 1 liter over 1,000 milliliters. Now I can get to grams. I've got 1 milliliter is 0.692 grams. That's my density. Okay. Now I need to get to this, right? So I'm going to use a ratio, right? I have this for 1 mole, so I need to get to moles, right? So I need a mole on top, and I need to calculate that, right? So 8 times 12 plus 18 114, we'll get something like that. Right? And now I've got a ratio, right? 1 mole of this is going to produce 5,461 kilojoules of energy. So I've got 1 liter. Based on converting to milliliters and density, that gives me grams. Now I can get from grams to moles. I can get from moles to kilojoules based on that known. I don't actually have to carry out this reaction. I know that I have this. This is how much energy is produced. So you run those numbers, and what do you get? There you got it.
I got 33,149.23.
Which I assume is 3.31 times 10 to the 4th kilojoules.
Yeah.
Okay. That's it. All right. Let's do another problem like it. This one's actually easier. How much heat is produced from the combustion of 125 grams of acetylene? Acetylene, the chemical formula is C2H2. Now, we don't have to worry about a density here because it's giving it to us in grams, right? So I can go straight from 125 grams, right? And I can start going, all right, I need to get to moles, right? So 125 grams times,
1 mole.
and then C2H2. So that's what, 24 plus 2 is 26? 26 grams per mole. Okay, so that gets me into moles. And now I know I can look over here. I can find acetylene, and it tells me that 1 mole of acetylene will yield, where'd it go? 1,301.1, sorry, negative, kilojoules of energy, right, of heat. My grams will cancel, my moles will cancel, I'll be left with kilojoules. So it's 125 times 1301.1 divided by 26. And when you run that math, you get we will stop here. So the next unit will need to just be in. Okay. All right. Y'all have a good day. I will. Today Wednesday. I won't see you until next week. Y'all have a good week. Good weekend.